To a club. So we have a double integral over the interval of first CD, then AB, of the sum of two functions, single variable functions, but one as a function of X and the other as a function of Y. All right. Then what's going to end up happening is once we work that, we're going to get two possible outcomes. So, I mean, because I got to admit, when I first saw this problem, I think I got this from, the Larson textbook, the old calculus, multivariable calculus textbook. I might be wrong about that, but I'm pretty sure that's where I got it from. I remember looking at this being like, that's a juicy one. I better put that in the notes, a long time ago. But then I also thought to myself, I'm like, that's a scary looking one. Like I'm not looking to intimidate the living daylights out of people just by having its mere presence on a handout, but it is a scary looking one. But if you take it a chunk at a time, a piece at a time, it gets a little bit easier. Now I know that what a lot of people like to do when they develop a proof is they they work from the end to the means, the ends to the means. We want to go from the beginning to the end, just because that's just the more authentic way of handling the proof, or at least the rigorous way. So what we're going to do is evaluate it the way we handled every other double integral. Inside out. All right. Now, the good news is, or one bit of good news, there's lots of good news. But if I can categorize all the good news into one group, that group would be, or that group would have a title of Calc 1 rules still apply. All right, Calc 2 rules still apply. And that would be, in this case, if I have something like the antiderivative of a sum, I can take the antiderivative of each piece of that sum separately. All right, so I'd be looking at the integral over the interval of c to d of f of x dx, I'm sorry, dy, plus the integral over the interval of cd of g of y dy. All right, now, well, we'll still worry about the outer component there. We have another integral to take, but this is enough as it is. So this component, overuse the word, you can always tell going into a lesson what word I'm going to overuse that evening. But this is a function of x, and we're integrating with respect to y. So this f of x is treated as constant. So the antiderivative of this is going to be f of x times y over the interval of c to d. Now, the other piece we really can't do anything with. The only thing that we could actually do if we wanted to be particular about it, and the only reason I'm not going to do it is because I know where the story ends. We've seen what our ultimate objective is. You could, when you anti-differentiate a lowercase g, you could represent it as an uppercase g. All right, you could write, and I'll just make a note of it. All right, so could write as g of y, capital G of y, over the interval of c to d. All right, in which case you could actually go even further and call this capital G of d minus capital G of c. The only issue is that, like, you get stuck at that point. There's nothing else you could do. Right, my voice keeps cracking. Right, there's nothing else you could do there because we don't know what G is. Right, we don't know what C and D are. So that's as far as we'd be able to go. So it's kind of like a question of what would be the benefit of doing that. Maybe you prefer it in that notation, but since we know the way the proof is going to end is highlighted in yellow and green, then we might as well just stay with what we're doing, right? Now, what we are doing will allow us to manipulate this one a little bit further, right? So f of x, now we're subbing in for a y, because remember, when you're integrating with respect to a variable, the bounds are in terms of that variable, all right? So this is the same as saying y equals d, y equals c, all right? So that's a key ingredient telling us that those values d and c get subbed in for y, not the x. All right, people have struggled with that in the past, and I figured it would be worth making a point of. So f of x times d minus f of x times c, and then we still have the plus business here, all this other stuff. All right. Now there's a common f of x. So we pull that out. Pull it out just like a GCF. And then when you do that, you have a nicer, I guess, looking expression. I mean, I wouldn't call it beautiful, but you know, it's something better than it was. Now we have not taken the antiderivative with respect to x yet. Right? Just when you thought you were finished. No, it's really not that bad. Because there's really not much you can do, right? Because I can take the antiderivative of this whole thing with respect to x. But remember, the antiderivative of a sum is the same as the sum of the antiderivatives. So the antiderivative of f of x times d minus c dx plus the antiderivative. Now this antiderivative is over the interval of a to b, so I can tuck that in there. I'm only doing that retroactively because I forgot to write it the first time. Okay. But then I'm still taking the antiderivative with respect to x after I'm taking the antiderivative with respect to y. So this whole thing is still coming along for the ride. All right, and so I'll have a little dx on at the end. And then really the only thing that's left in order to get it in the same form as that yellow highlight up there is just to factor out the d minus c from the integral, because there's no x in there, so it's unrelated to the integral. Right, so I can write it as, I'll just do a quick copy paste. And there you go. Right, now a natural question could be something along the lines of, all right, well, that's the yellow one, but how do we get the green one? Do we now have to like simplify this further in order to get the green one? I mean, that sounds like it would be crazy. What I'm going to do is I'm just going to move this out of the way for a hot second. I'm going to take a snip of this. And then I'm just going to put this back in. Don't need that to be so big. So I'm basically going to take it back to scratch and write a big old or. Now, one thing that we're going to learn, well, kind of tricky because we've already done some of page 67. So sequentially, pretending as if page 67 never happened, one thing that we're going to learn is that under certain circumstances, you can reverse the bounds of integration. I'm sorry, not reverse them. that really is Calc 2. You can reverse the order of integration, right? So instead of dy first, then dx, we can do dx first, then dy. We do have to learn under what circumstances that will happen, or that's allowed, but that is something that could come into play, right? It turns out that one of the conditions that allow you to reverse the order of integration is if you're dealing with rectangular bounds, right? So a rectangular base area. So this is thought of as, okay, I don't know how that, oh, just a double tap, that's it? Okay, that's what's happening. All right, got to the bottom of that finally. So this is really y equals y equals. This is really x equals x equals. So just focusing on the bounds. If I create a graph, and I'll just do it in the first quadrant of the XY plane, just because I want to keep it as, what the hell? I want to keep things as simple as possible. Here's X, here's Y. Let me plot X equals A, X equals B. Let me get a Y equals A, Y equals C, Y equals B. All right, so what we're looking at here is a rectangular base region. All right, and what I mean by base region, because you look at it and say, well, this doesn't look like much of a base. What that is we have a top view. You know, we're looking down upon the XY plane from some point in space, right? And so when we look down, we're seeing a square region. Well, in this, I made it look like a square. It's really rectangular, all right? But what's happening is you have some sort of three-dimensional surface that's kind of hovering in space above it, all right? So I'll just make some sort of three-dimensional surface. You have that three-dimensional. I just can't get out of my own way today. Hold on one sec. Some three-dimensional surface is just kind of hovering in space above that, right? So let's say, you know, let me shrink that down a little bit. Too little. Let me kind of shade it in a little bit, make it look a little nicer. Actually, let me do it in a different color. All right, so this three-dimensional surface is hovering over that base region. All right. And so in doing so, it creates a volume. That volume is based off of a rectangular solid everywhere except for the top, right? At the top, it follows the contours of the surface. Right, so the top here follows the contour of the surface, but below that, it's rectangular. It's a rectangular solid essentially. All right, so you have this surface that's floating, flowing, however you want to say it, in space. Below it, you know, it's just kind of, think of it as like columns holding up, you know, as corners of that rectangular region, the surface, the volume that's contained within there, right? If you have a rectangular base area, then you can, if you want to, reverse the order of integration, right? So because it's rectangular, you can swap these around and make it go from C to D, then A to B, same functions being added, but then dx dy. All right. So we're just basically going to do everything we just did again, just a little bit quicker. And, you know, from the perspective of experts, right? So if I anti-differentiate, and you can also kind of skip a few steps along the way. You don't have to rewrite it separately. So we're anti-differentiating the f of x. That I'm just going to leave as the antiderivative from a to b of f of x dx. The g of y, I can anti-differentiate that. That would be g of y multiplied by x over the interval of a to b, which then in turn, let me just copy paste this. Becomes g of y times b minus g of y times a, which is going to become g of y times b minus a. All right. Then carry through the next level of integration here. Where we integrate with respect to y over the interval of a, c to b. All right. So we get our double integral. C to d, a to b, f of x dx, then dy, plus the antiderivative from c to d of g of y times b minus a dy. And then, you know, just pull out the b minus a and you're done. All right. So just like before, it's a matter of a little quick copy paste job. We'll switch a Ruski. And you can see, you know, if you, well, maybe you are very particular about this. Some people are, and that's okay. It's not exactly the same as the green highlight. I got to swap the order to be exactly the same, but it's virtually the same. Right, so, you know, for the sake of having that QED moment, we proved what was to be proven, whatever the right word is. We have it at this point. All right. So it's a rigorous proof, but it's getting at the idea that the sum of two functions anti-differentiated over the interval c to d, then a to b, would follow either of these two models. And you look at it and say, okay, well, how is that any better than what we were, you know, like than doing it just by hand? Well, you kind of look at it and say, well, what if you have a function f of x that you have absolutely no idea how to anti-differentiate, but your g of y, you're very confident about. You're not gonna have a problem with that. Then that yellow one is looking pretty good, right? Because that's all calculated. So you look at it and say, well, if I know that that's equivalent to the one in yellow, I don't have to work with it as is. I could just manipulate it to be in that other form. And I could save myself a lot of work, because then the only part that I'd have to worry about actually carrying out by hand even a little bit would be the g of y part. Right? Maybe that's something I can handle. Or maybe you have absolutely no idea how to handle the g of y part, in which case you go to the green one, let the calculator do that part, and you just worry about the f of x. All right. So that's a practical reason why you might want to know some rules like this, why you'd want to prove it. Now, I like this because it's a nice, elegant way of it's not proving Fubini's theorem. It's not proving that the order of integration is interchangeable, but it is giving us another example of an instance in which the order of integration is interchangeable. All right. So this is telling us that if we interchange x and y, dx and dy, for the sum of two single variable functions, one with respect to x and one with respect to y, that Fubini's theorem is going to be in play. It's just these expressions are going to be equivalent to each other. They just look vastly different, but that's fine. A lot of things are equivalent but look different. 360 degrees looks very different from 2 pi radians. Right? We don't care what it looks like as long as we know that they're equivalent. Right? So again, I kind of hand waved over 67. I said this is very textbooky. Read through it if you like. I kind of have the expectation or the understanding that, some people are really good pulling information from a textbook, and some people are they're like, listen, I'm taking this class because I can't do that. Like I need you to interpret it for me. So either way, right? But the notation here is kind of funky. It says f of x sub ij, comma, y sub ij. Those are talking about Riemann sums in a particular sequence, right? So the first, the second, the third rectangle going in the x direction would be the sequence of I values. The first, the second, the third, and so on rectangles going in the y direction would be the sequence of j values, right? But what's happening here is if you just kind of look at it and say, all right, if we go a certain number of rectangles, just think about this as if you're sitting in Calc 2 and your teacher's hand waving their way through Riemann sums like mine did. I don't know. Everybody has different experiences with that. It's kind of tricky because I've taught this class enough where I have people who come into the class and say, you keep saying Riemann sum. I have no idea what that is. And then I have people saying, yeah, I remember Riemann sums. Our professor spent like half the semester on those dang things. And so everybody kind of falls in the middle somewhere, I would imagine, right? I'm just taking a moment to admire the fact that curve actually came out the way I wanted it to. That's a shocking revelation. But anyway, whether you only touched on Riemann sums a little bit or you went into full-blown proofs in Calc 1, Calc 2, you probably got the idea of rectangular approximation out of it, where you're looking at over an interval the idea of creating as many rectangles as you can in order to approximate the area under a curve, right? So that's what we would do here. And so what I'm going to do is just focus on the rectangles that would jive with the grid at the bottom. But this would be one rectangle. And whatever area I would compute out of this would be an underestimate of the area under the curve because I'm missing some triangular spaces. I'm not getting any of this stuff here, right? So there's some area that's being excluded, but that's okay because that's where the concept of a definite integral came in, where you limited the width of the rectangle as the delta x, that little horizontal change approached 0. Then you got in more and more rectangles, and therefore you ended up getting more and more of an accurate estimate of the overall area. Right? So that part always kind of, well, I would say it always worked out in the sense that most students, even if they didn't really understand a lot of the other theory that was involved in Riemann sums, they at least understood that part. Okay, yeah, if we make them skinnier, we can get more in. All right. My professor back in the day used sardines as an example. I was like, I better go look up what a sardine looks like because I have no idea what the hell you're talking about, dude. But then I saw, I was like, whoa, that's pretty freaky. Put a little tiny fish in a can. I'm like, oh, that's crazy. All like neatly lined up in a row? If it wasn't so like horrific to think about, it's actually kind of cute. All right, I think I bought myself enough time. And I just blab on aimlessly till I finish drawing what I'm trying to draw. All right, so if this were a Calc 1, Calc 2 class, then we would find the area of each one of these rectangles. You know, if we were just trying to come up with an approximation, add them all up, and we'd say, okay, well, the area is going to be somewhere in the neighborhood of whatever the sum of these areas are. All right, so that's great. But what's happening now is we have some depth. Each one of those rectangles has some depth to go along with it. Right. So if I want to get a truer estimate of the volume under the curve, I would want to, and there's actually a couple of ways we could do it. We could actually get like little cubes and give them height, you know, project from the little cube up to the surface, or we could travel the length of the slice. And this is what we were talking about last time, where I say, if we propagate outward from here, you know, take our single slice and then just kind of work our way down the line from there, then what we would end up with is a true estimate, or relatively true. I mean, it all has to do with, you know, how many of those rectangles you were able to get in there. But if we were to work our way down the line, then we would have a pretty good estimate of what the overall volume is. All right. So we have this function up here, this whole thing, that's our z. All right, so that's the cap on the whole thing. All right, so going in a single direction, we want to get an area. All right, so an area would be associated with each one of these little rectangles. All right, that area would be a dx multiplied by z. All right, and so we would be saying the integral over the interval of, you know, we're talking, oh, I did it, dang it, I did it the wrong way, I did y. All right, well, we're doing y first. It is a rectangular base region, so we're good to go there. All right, so over the interval of c to d, we'd have our function z integrated with respect to y. All right, so you just got to kind of think about what that means. It's only the height. So it's only the height of this rectangle multiplied by the length of the base. Now, if I want to get some depth involved, what I would need to do is take that and integrate it with respect to x. All right, I want to integrate it down the line with respect to x. All right, so every one of these little, because I kind of painted myself into a corner here, I'll just start off here. These little tick marks corresponds with a cross section going in the opposite direction, or the orthogonal direction, really. I might be able to, nah, it's not even worth it. But each one of these little distances represents a dx, and that's spanning the distance from A to B. All right. And so that's the idea behind the volume. But really, if you think about it, what are we getting out of this? We're getting z times dy times dx, all right? So the z represents the height. The dy, we can call that a length. The dx, we can call that a width. Height times length times width, or quality, or height times width times length would both give you volume. Right? And so that's kind of a more intuitive justification, because really what we're doing is we're getting the volume of a rectangular solid. Now, I drew it so that it traced the actual curve here, but really what would be happening is if we were estimating the height at a particular moment, or a particular point, that height would actually have a horizontal distance associated with it. And we would still be using rectangular approximation, but this time it would be rectangular solid approximation, right? It's just, it just looks terrible, the diagram, so I didn't do it that way initially. But it really is height times width times length, using this to approximate the volume. And as the dy's get smaller and smaller, as the dx's get smaller and smaller, then the little square bit of surface of intersection with the surface gets smaller and smaller, and that actually ends up being a better approximation of the area of that surface, giving you the overall volume, right? And so because these two things are interchangeable, because it is rectangular, that allows us to say that the opposite would also be true. All right. So it's a little bit more on the theory behind it. I know that that it tends to, in a lot of cases, fall on deaf ears, just because honestly, there's no guarantee that a lot of people are listening. But aside from that, I'll be hopeful. It's theory. And people want to get into the practical. They want to get down to business and start solving problems and stuff like that. But if you have a true understanding, I mean, you know how it is, especially after volumes of revolution in Calc 2. If you have a good understanding of the underlying principles, then you don't have a problem setting up these integrals. It's going to be really easy. All right. So just something to keep in mind. So on the next page, we talked about that one problem where we went in a couple of directions. We went with respect to y first, then with respect to x, and then we switched it around. There was a lot of hand waving and crappy drawings, as you can see, but now we have a little bit more of a foundation. It should be a little easier to understand why we're doing what we're doing, right? We're also going to see that there are some circumstances where we just would prefer to integrate one way as opposed to another, right? So compute the exact volume of the solid bounded by the surface. Oh, you see a little font issue there. Above the region, and that region is rectangular. In fact, it's a square region in the XY plane. Okay. And so what that tells me is that I could just kind of jump right to it and say, all right, I'm going to take a double integral over the interval of -1 to 1 of my z equation, which is x squared plus y squared, and integrate that with respect to y first, then x. Or I could go the other way. That's not an x. Or I can go the other way and integrate first with respect to x and then y. Either way will work, and we'll actually do it both ways, just so you could see. I mean, there's a reason why I put this example. And you'll see on the next, I think it's the next page, where there's an example that's pretty similar, except the base region is not rectangular. So an adjustment would need to be made. All right. There will always be a circumstance in which you're able to reverse the bounds. I keep wanting to say that. Reverse the order of integration. It's just how that will impact the bounds of integration. That's the important lesson to be learned today. All right. So I'm going to integrate with respect to first y, then x. So x squared y plus 1/3 y cubed. And that's over the interval of -1 to 1. All right, these are y values. This is y equals 1, y equals -1. So those are values we plug in. Plug in a y equals 1 first. That's easy. That's x squared plus 1/3 minus, plug in a -1 for y. That's going to be negative x squared. And that's going to be minus 1/3. So negate, negatives make positives when you put them together. 2x squared plus 2/3. Now I'm going to integrate that again, this time with respect to x. Easy enough to do by hand, but I don't want it. I would go with you, but I don't want it. Movie quote. So 2x squared plus 2/3. Making sure I'm typing it in correctly, which is always my issue among the 17 other things that are my issue. Dx, 2 2/3. All right, if you want a math bracket, just so you can take a little bit of thinking out of it, by all means, I respect that. Going the other way, we're looking at 1/3 x cubed plus y squared x over the interval of -1 to 1. You see it's got the same ingredients, so it's going to shake out in a similar fashion, if not exactly the same. All right. So I plug in a 1. Now these are x bounds. So far, it hasn't been too much of an issue keeping track of the nature of the bounds, whether they're x bounds or y bounds. I'm going to tell you, as soon as I stop making all this crazy noise getting Calc out, I'm going to tell you, it's going to get more and more complicated and more mind-bending and more important to keep track of that sort of thing. All right. So it's a good habit to start building. In fact, there will even be a point where some of us are going to want to, myself included, are going to want to even label the integral with the appropriate variable as the bounds. Instead of saying -1 to 1, I'll say x equals -1, x equals +1. Right? It'll make it easier to keep this stuff straight. All right, plugging in the ones, you get a 1/3 plus y squared minus, plug in a -1, you get a -1/3 minus y squared. All right, real quick, the appropriate number of mix. So 2/3 plus 2y squared. All right, and you see it's the same ingredients. There's no reason to think it would be anything different. It's the same expression integrated over the same interval. The only difference is the variables. So it's going to be 8/3. Whether you want to show the work or not is up to you. Now, if memory serves, if you need the peace of mind, it doesn't always work for every variable, but for the y's and most letters that Desmos recognizes as a variable, it'll still do the correct calculus. All right. So you could, for peace of mind, if you want to put it in terms of y, you can. Nothing wrong with that. All right. Page 69, another little proof there. This is a good puke. Good puke. Huh. I wasn't really gonna say puke. I was gonna say good puke, but then I was like, you know what? That's not even a word. I'd actually rather say puke. Yeah, it's a good puke. It's a good bit of throat. No, there's no such thing. Yeah, I just I meant to say proof, and I said something else, and it's pretty terrible. It's not as bad as what happened today in school, in the high school, where I was on the Zoom and I had to log into my Desmos account. And for whatever reason, I was using the new browser. So I had to log in, like fully, like with the username and the password. And it didn't occur to me that, through the Zoom, I mean, it occurred to me that people would see me logging in, but it didn't occur to me that it was doing that thing where when you type in the password, it shows the letter, then it changes it over to a black dot. So you put the first letter in and it changes over to a black dot. Second letter changes over to a black dot. Like whoever thought that was a great way of keeping your password secure, I don't even know. And I didn't even think that was still a thing, but whatever. Anyway, I start typing in the password, and because every time I get an alert to change my password, I get more and more aggravated. So my passwords get more and more profane. Like this one was pretty bad. And I didn't realize that, well, at least until I heard all the giggling, that they heard what my password was. And I can't even say it because it's like really bad. But not like disrespectful bad. Bad as in like just inappropriate. Anyway, so yeah, I have done worse. I've done, let me say puke, I guess. Anyway, it's just one of those days. Prove was the word I was looking for. And you know what? Prove is now the word of the day. And prove, the word of the day. The volume of the cube formula is V equals S cubed in R3. All right. So V is equal to S cubed in R3. All right. It doesn't seem like you're really given much to go on here, but what we want to do is come up with an expression in general terms that we could use to find through the multiple integration techniques a result that gives the volume of a cube in 3 dimensions. Right? So the first thing I'm going to do is, just because I feel like there's so much space here, it's like begging me to draw a diagram. Oh, I'm going back to Calc 2 with, well, it was a different concept. It was different time. Volumes of cross sections. The perspective drawing I was about to do, it wasn't going to be pretty. All right, so X, Y, Z. All right, I want to define a cube. All right, so that cube I can let have some Z value equal to whatever I want. All right, as long as all 3 sides, all 3 important edges are equivalent in length, we're fine. So what I'll do is I'll call this side here S. And so that would force this side, if it's going to be a cube, this side and this side to each be S. And so perspective drawing. So what I'm going to do is I'm going to create my bounds. Now, because it's a perspective drawing, got caught between drawing and diagram. We know that we're going to have a rectangular base region. It just looks like a parallelogram. That's right? So in terms of x, we're going out from x equals a to x equals b. I'm just keeping it like the rule, basically. And then we're going from y equals c to y equals d. Now, the c value, well, you're just thinking about where it actually is. Y equals c is actually going to be equal to 0. Right? Because that's actually the x-axis. If I'm going out s units, then y equals d is actually going to be equal to s. So y equals s. Right? Same idea for the x equals a. X equals a is actually on the y-axis. So x equals a equals 0. X equals b is going to be equal to s again because there's s units away. So then all we would need to do is define some surface z that's actually going to have a height of s off of the xy plane. So we want a surface z that is parallel to the xy plane with height of s. Well, that's actually just the definition of a plane. You know, your most basic plane, the one parallel to the xy plane, is z equals s. Right. So I mean, if you want to get a little sketch in there, you can, but you don't have to go too crazy because we didn't even really need a diagram to begin with. But you know, it just kind of felt like a diagram situation. So I'm just taking this plane here and I'll just kind of throw it on up here. I'll just kind of sort of have it living in the, it's not really parallel. Let's see, I need it to be at least somewhat parallel. Yeah, something like that. It actually looks just god awful that way. So, you know, maybe we're better off not having it there. Okay, but what I can do, just to kind of make it look at least something like what we're trying to get out of this, I can at least draw the corner posts. This way, when they intersect, it'll be it'll at least just be a little bit of a subset of the entire plane. All right, so this would be the plane. I'm just going to kind of live with that one. Get rid of that one. Let me just kind of move this over. I'll just put it here. I just want to get a little shading going on there. And so this guy over here is z equals s. All right. So that's, at least as far as the diagram is concerned, a pretty solid setup. You know, it's not too bad. I mean, the picture is, you know, it's the best I can do. So we're just kind of always limited to that. But we have our bounds. We have our z equation. We know that if we want to integrate, if we want to find a volume over a rectangular base region, that it's over the interval c to d, a to b, or vice versa, doesn't matter, of some function z, dx dy or dy dx, it doesn't matter. Again, it's just if you go c d a b, it should be dx dy. because the dx should go hand in hand with the AB, and the dy should go hand in hand with the CD. All right. So our bounds are going from 0 to s. And z is actually equal to s, so I can make that substitution. Dx dy. All right. So the antiderivative of s with respect to x is sx. Now this is over the interval of 0 to s. So we're talking s squared. All right. So what I would actually do here is take a quick look and see what is this really giving me? Two, Pablo, two. All right. So we're going to integrate this s squared over the interval of dy, over the interval of 0 to s with respect to y. But that s squared, again, we want to think about what that means. We just integrated a height of z with respect to x. So meaning based off of some horizontal change in x going from A to B. All right, so if I bring it in on this diagram here, what I'm looking at here, so here's A and here's B. We're starting off here and using rectangular approximation. You see, this is why I have to take forever to draw a diagram, because when I try to not take forever, it just ends up being so indecipherable that it's like, it's not even worth it. All right, so I'm just giving this a Riemann look. Just giving it a little Riemann look. The horizontal distance here for each one of these rectangles is the dx. All right, it's an infinitesimal movement along x, and so if I just kind of mark off one of them, actually, let me get a clean one. I'll take this one. What I'm getting is the area of one face of this cube. Well, that's great, because now you know how you can actually prove using integration the area of one face of a cube, or area of a square if you want, so that's nice. 1/3. I'm sorry, I was going to say 1/3 s cubed. It's not that. It's s squared y over the interval of 0 to s. Right, this is with respect to y. So s squared is treated as a constant. So s cubed would be the result. And so that's what would happen if we took each one of these regions, one of these slices, and propagated it over the interval of C to D, covering the distance in terms of y. All right, so each one of these little rectangles that would be in the opposite or the orthogonal direction, making a cube. I'm sorry, not a cube. Well, it would be a cube with height, but it would be each one of them is a rectangular solid. And we're just taking each one of these and building them along the way until we have at least one piece of it. So that's one row. And then, so that's our D. Each one of these would be a dy. And then we just kind of work our way down the line. So each one of these slices cross-sectioned with y, with the dy, gives us a volume. And then we move down to the next row, to the next row, to the next row, to the next row. And then we have the overall volume of the entire figure. All right, and so that would be the volume of the cube is equal to s cubed in R3. And that would be your proof. Now, as far as the proof is concerned, it's only this stuff here that's the proof. Which starts with the letter P, not the letter R. All right, so this is your actual proof. Everything else is really just kind of justification, but it's kind of getting at the idea of like, well, how did you know to do the stuff on the right without the stuff on the left? All right, so, you know, without really spelling it out for you, I'm basically saying if this problem ends up being the proof on the test, if I see the stuff on the right without any of the stuff on the left, I'm calling BS on your response. And then it's just like, you just copied. You copy without knowing what you were copying. I need something to indicate that you kind of know why you copied what you were copying. All right, so hopefully that was interpreted correctly. All right. So then on to page 70. It's again, just like page 67, there's a whole lot of notes. And those notes are all textbooky. You know, you have linear combinations, double integrals, really intimidating looking stuff. You got the double integral over a region with non-constant bounds in the x direction. You got rules upon rules upon rules, and they're all just wonderful. I think they're better understood through example. All right. Now the linear combination stuff, that I think is sort of in the neighborhood of self-explanatory. Right? If you just read those, you kind of look at it and say, oh, okay, that sort of makes sense. But it'll come through in the examples. Right? So number 4, compute the double integral of the function over the region bounded by the curves y equals 1 minus x squared and y equals x squared minus 1 in the xy plane. All right, so the first thing I'm going to do is actually draw those two quadratic functions. All right, now I already have the diagram there. You know, those two little black curves at the bottom, that's the base region. What's happening is that's actually propping up the whole thing. If you kind of look at this as, this is the strut or the post or the, whatever, holding up the surface, and you just kind of work your way around. I'm just going to kind of line this up a little bit better. Bottom line is you have all these different lengths associated with the surface itself, because we're not going up to a plane that's parallel with the XY plane. But also, it's definitely not a rectangular base region. All right, so there's a lot of funny business going on here that we have to account for. All right, and that has to do with this interval, or the interval associated with this function. All right, so if you get in the habit of saying, well, it's going to be z bounded between this and that, dx, dy, and just call it a day, then you're kind of setting yourself up for trouble. You want to be thinking about why the bounds are what they are. All right, so let's take a look at this. I'm just going to snap it and bring it in so I can mark it up. I'll save it. Why not? All right, so this is the figure. Let me do that. Underneath, oh, the figure is the three-dimensional surface. Underneath that is that base region that looks almost like it could be elliptical, but it's definitely got a little funny business going on. All right. So this is going to dictate the bounds of integration. All right. So what we have to do is figure out what this means in terms of an X and Y set of bounds. All right. So we know that we're going to have a double integral. We have no reason to think otherwise. We know that Z is the height. Z is variable, so it's not going to be as clean as a parallel plane, but it's still going to be Z, right? Our concern is whether it's going to be a dx dy or a dy dx. So in the absence of a better idea, I'll just say dx dy. All right. So what that would mean is that we'd have to focus on the x bounds first. All right. So if I were to look at just the x values, we'd immediately have a problem. All right. Because what I can't say, if you look at this and say, well, it goes from -1 to 1. Well, what that would mean is that it actually went from -1, as in x equals -1, to 1 as in x equals +1. Now, does it really? I wouldn't say so, because what that would do is it would cover everything between -1 and 1, from -infinity to infinity. So this would go down forever. It would go up forever, right? So without restriction. So that would be a problem. So then you kind of think to yourself, all right, well, if we could cap it, that would be pretty good. All right, so what if we were to say, all right, yeah, we're going to go between the x values of -1 and 1, but only between y equals, let me get the green up. I hit the wrong thing. Yeah, look at this, algebra 1. I'm doing the same stuff. Same but different, right? That's always how it plays out. Y equals 1 minus x squared on the high side, and blue. What's that, like the good blue? Oh, there it is. It's still not the good blue, but whatever. X squared minus 1 on the low side. So what if we were to say that we're going from y equals x squared minus 1 to 1 minus x squared? Right? That gives us the flexibility to not just be between two fixed values. Right? So if I were to say that y is going from -1 to 1, I'd be saying that we're going from here to here. And so we'd be back to what we had with the other problem, some rectangular region. We don't want that. We want y to be between two bounds that are variable in nature. All right. So if you kind of think about it and say, all right, well, from my y bounds, I want it to be between x squared minus 1 and 1 minus x squared. Be like, all right, that sounds good. But then for my x bounds, now I have to restrict that further, because if I don't make a good restriction, then I'm saying that this could go from -infinity to infinity. All right. So if you kind of look at this, there's a lot of instances in which the curve goes above y equals x squared minus 1 and below, well, not really. I was going to say below the green and above the blue. It's actually only, there are plenty of instances where that happens. This just happens not to be one of them. But basically what we're looking for is an inequality relationship, something like this, if I cap it the right way, then what I would be doing is saying, all right, I'm only interested in the part of the graph that exists at those intersections. All right. So if I can actually truncate it. I always get this confused with the algebra. There's a conditional way of truncating it. I just can't remember. I just can't remember it. So I don't want to go down that road. But if we say that it's going to be above the blue, below the green, we're capping it at the ends by saying that that's got to be between -1 and 1. All right. Now, we may run into an issue here, but let's actually play this out and see how it goes. And I'll show you. Long story short, we are going to run into an issue that we're going to have to account for. But I'd rather run into the issue, show you why we ran into the issue, and then how to fix it. All right. But let's say we go like this. We know that z is equal to x squared minus x squared plus y squared. All right. So let me do that. All right. Now you may already be able to predict what the problem is going to be, but let's say you don't know. All right. So we would integrate here. It would be 1/3 x cubed plus y squared x over the interval of -1, 1. All right. So then we plug in. We've already done this problem before, at least this part of it. All right. So it would be 1/3 plus y squared, because with respect to x, these are x bounds, plus y. Oh, I don't know why I said plus. I already did that part of it. Minus -1/3 minus y squared, which would give us 2/3 plus 2y squared. All right. All sounds great. Now we bring in the next layer here, where we would integrate over the interval of x squared minus 1 to 1 minus x squared with respect to y. Now, if you get beyond this step before you realize that there's going to be a problem, then, well, I guess enjoy the ride, enjoy the learning experience. There is going to be a problem because we're going to now integrate and substitute, once we use our fundamental theorem, we're going to substitute a variable expression in after we've integrated, which means that our answer is going to be in variable form. It's like, how do we get a volume if we don't have a volume? If we don't have a number? We should get a numerical answer, right? So what we need to do here is create a restriction to our restrictions. All right. So that's the thing that you kind of gotta kind of wrestle with in your mind, is the order of integration definitely, absolutely, without a doubt, matters here. It's just, which way do we go? Well, as it turns out, we should have gone the other way. And I'll show you why. If we restrict, right? So if we restrict from -1 to 1 first, right? Some function, -1 to 1 first. Numerically, that as you can see, it played out. It gave us something that was easy enough to work with, but then it converts it over into a variable expression after the fact, right? But if we restrict y to be between x squared minus 1 and 1 minus x squared, then restrict x to be between -1 and 1. What we're doing is we're creating a domain for first the y, then the x. All right. So it's kind of like, when you're dealing with a multivariable function, you want to make your restrictions, but one of them is a restriction upon the other. All right. So the y restricts the z, the x restricts the y. All right. But only because it's numerical values that make up the x restriction and variable quantities that make up the y restriction. All right. So if you don't have that information, then it becomes a little bit of a different situation. Like if you don't know going in, like if maybe you don't have a graphing utility or something like that, then it's a different story. But I can't imagine you'd be in a situation like that. So it's kind of like that's kind of like an old school problem. So what we would do here is integrate from -1 to 1 as the second set of bounds. But prior to that, it would be x squared minus 1 to 1 minus x squared. Still the same function. Dy dx. All right, so we're still going to integrate the same way we did before, except now we're going to have variable bounds. But that's going to be okay because after the fact, we're going to be replacing those variables. Even though the anti-differentiation may be complicated, we're still going to be able to get some clean values because we're just going to let technology do the work for us. All right. So x squared y plus 1/3 y cubed over the interval, and this is where it gets gross, of x squared minus 1 to 1 minus x squared. That's what gets substituted in for y, right? So that's not going to be pretty, but we could write it as x squared times 1 minus x squared. You could also factor and things like that first if you think it could help, but it's not really necessary because the tech is going to do it all for us. Right. So then from this, we subtract the same stuff, just replacing the y's with x squared minus 1s. So x squared times x squared minus 1 plus 1/3 times x squared minus 1 cubed. I would probably, even though we're going to type this into Desmos, it's almost like required at this point that we simplify it at least a little bit, just because it is a lot to type in, So, whether you want to distribute and things like that, like full blown, different story. That I leave that up to you. But at a minimum, let's distribute the negatives here. For the negative. All right. And then integrate that over the interval of -1 to 1 with respect to x. And it's a fair amount to type in. I don't know that we want to do that. So you may notice here that these are opposites. What I'm underlining, the 1 minus x squared and the x squared minus 1. If we factor out a negative, that could actually clean things up or help clean things up a little bit. I rewrote the same thing a second time. I have no excuse. Okay. I could factor out a negative from this one also. A -1 3 times, I would factor it out. So this would be minus 1/3 x squared minus 1 cubed. Then I would have a minus x squared times x squared minus 1 minus 1/3 times x squared minus 1 cubed all dx over the interval of -1 to 1. Right. The benefit again is now we can combine some terms, and we'd be looking at going from -1 to 1, -2 to -2x squared. times x squared minus 1 minus 2/3 x squared minus 1 cubed dx just makes it a little bit of an easier ride when it comes to finding the antiderivative. You know, it's just, I mean, if you're fine typing all that stuff, all that stuff in red in, by all means, go for it. But we know it could be a little much. That's going to be cubed. All right, now I'm just going to double check. Oh, that's lovely. Oh, I see what happened there. I'm like tapping on it too rapidly. Yeah, I think it's good. So about 1.143. Right, so all that for such a small number. Like, oh, okay. So this is an instance where you actually had to go in one direction as opposed to another, just because that's the way that the situation played itself out. So you had variable bounds in one direction and numerical bounds in the opposite, or the orthogonal direction. Now, if you wanted to, some people do this, and it's fine. There's nothing wrong with it. But they would solve for x in terms of y. You know, so find the inverse function of y equals 1 minus x squared and y equals x squared minus 1, and then get y bounds that are numerical. It's something that you can do. I just don't recommend it because you're taking something that's polynomial and making it a root function. It just makes it more complicated, you know. So it's just, you know, in a lot of cases, it ends up being just kind of like a personal preference. But in that case, I think you're just making life more difficult. All right. So the next one, computing the double integral, so the z function over the curves x equals y squared and y equals 2 minus x in the xy plane. So it's the same general idea conceptually. All right. So get rid of this. I can put in my equations. Good thing about Desmos is that it can handle inverse equations or inversely defined equations, as well as your normal y in terms of x. All right, so that's what we're up against here. Now, in terms of how this is defined, there seems to be a little disagreement, because we have x solved in terms of y for the x equals y squared, but then we have y solved in terms of x. So which way do we go? You know, so if we're going to do this using a double integral, which we pretty much have to at this point, it's the only technique I've really gotten into. We have our 6 minus x plus 2y. That's our z equation. It really is a question of, am I going x first and then y, or am I going y first then x? You got to sort of let the function sort of take you where it's going to take you. Okay, because if you make a decision going into it, like, oh, I'm going to do x first then y, then you're missing the point. All right. What you want to have is a variable bound. Any variable bounds come first. Followed by constant bounds. All right. Now, this one could go either way, but x equals y squared is pretty not bad. right? In terms of how it's defined, y equals plus or minus the square root of x. I'm not really liking that. All right. How do I know plus or minus? Well, because we got an entire sideways parabola. If I had just typed in y equals the square root of x, that's only the top half, right? So I would actually need the negation, right? So I would actually have to have two functions to do the job of one, right? So a function of x in terms of y. So we're better off with the parabola, the sideways parabola written as x equals something in terms of y. So let's make the adjustment where we solve for x in terms of y for the linear function, right? So subtract the y, right? So x equals 2 minus y. Yeah. So just do a quick verification, make sure you got the right thing, because that happens sometimes, especially with me. All right. So now we're basically saying pretend that y equals 2 minus x wasn't there and replace it with an x equals 2 minus y. All right. So what we want to do is think in terms of lowest x to highest x. All right. So low bound to upper bound. Well, if we're doing it in terms of x, that means left to right. All right. So we're looking at the leftmost part of the graph. There's no disagreement. The leftmost part of the graph is always the parabola. So that's going to be x equals y squared. The rightmost is going to be the line x equals 2 minus y. All right. So that's a variable of x in terms of y. Solve for x in terms of y. So that means that we're dealing with a dx as our first integral. All right. Our second integral is now necessarily going to have to be in the form of dy. So it's going to be y equals one thing, y equals another. It's just a question of what they're going to be. Well, we could do it algebraically, but we could also just do a little tap on those points and determine where this interval starts and where it stops in terms of y. All right. So if we restrict the graph so that it only exists between the parabola and the line, there's a lot of portions of the graph that exist between the parabola and the line. You could have, well, I was going to try to, anything up here, anything between these points, that's between parabola and line. I mean, it would be a negative distance, but it's still between the parabola and the line. Anything between here and here, anything from here to here. But now if I restrict it by saying, no, I only want it from here to here. So I don't even want to look at that one, right? Then I'd be looking at a low bound of -2 and an upper bound of +1. All right. So those would be my restrictions. And now it's just a matter of just kind of diving right in, integrating first with respect to x. So 6x minus 1/2 x squared plus 2xy. That's happening over y squared to 2 minus y. All right. Not pretty, but doable. Because again, we're letting the tech do the work. So 6 instead of x, it's 6 times 2 minus y, minus 1/2 instead of x, it's 2 minus y squared, plus 2 instead of x, it's 2 minus y, times y, and then all the same stuff again, just with y squared. All right. Now just be careful about the instructions, because in this one it says compute the double integral, but some of them I just ask you to write the double integral. All right, so that's something to be mindful of. Right, you don't always have to compute it. I'm sorry, yeah, you don't always have to compute it. Sometimes you just have to write it. If it's a case where you just have to write it, you would stop at this step here. You would just write the double integral and be done with it. All right. So we do have to subtract off the substitution with y squared, but I'll get to that after I take a look at this question in the chat. If you're dealing with a three-dimensional functions, three-dimensional functions follow different rules. So you're talking about a function of three variables. So that's a fourth dimensional function. That's actually going to follow a different set of rules, but yeah, that's what you would do, right? It would be a triple integral with with constant bounds for the first integral and then variable. But you'll see that we kind of changed the rules of the game once we get there. Oh, why it's the upper bound, the 2 minus x, good question. So if you look at the graph on Desmos, when you read a graph in terms of x, I'm sorry, solve for x in terms of y, it's defined from left to right as opposed to bottom to top. So in the previous graph, it was pretty easy to see that the lower graph, was the x squared minus 1, and the upper graph was the 1 minus x squared, because it was like lower, physically lower, higher, right? But when it's defined as x equals something in terms of y, then lower is more to the left and higher is more to the right, right? So the graph that's printed on the paper doesn't really help us because the perspective is off. But if you look at the one on Desmos, the one that's to the left is the parabola, x equals y squared, the sideways parabola. The one that's more to the right is the line over the relevant interval. And so the low bound has to be x equals y squared. The high bound has to be the x equals 2 minus 1. All right, no problem. All right, so now we're going to make our substitutions again, but this time I'm going to replace, I've already copied, the x's with y squared. Let me just kind of clean it up. Start realizing after I do this copy paste stuff that it would have been easier to just rewrite it. All right, so that's -2 to 1, and it's now a dy. All right, so you can go through the process of cleaning it up. I lost some parentheses along the way here. Slash, I don't think I ever put them in. You can go through the process of cleaning it up, but it just strikes me as the kind of thing where it's not really going to clean up too much. So it's one of those situations where it's just kind of like suck it up and just start typing. Six parentheses 2 minus y.
Professor?
Yeah.
The third term, shouldn't we multiply by y?
Third term multiplied by y. Oh, I lost the y. Yikes, thank you. Very good. I appreciate it. Let me slip that in over here. I lost it in 2 places, it looks like. All right, hopefully that's good. All right, so then 1/2, 2 minus y, close it up, square it, plus, I'll write this as 2y, parentheses, 2 minus y, close it up, minus, parentheses, There's the first one I can just write as 6y squared. That's easy enough. Minus 1/2. To write that as y to the 4th. Then plus 2y to the 3rd. So a little bit of simplifying along the way. And then a dy out at the end. And 15.3 is what we get as a result after all that. That's one of those where you just got to kind of trust in the force, because yeah, it's a clean number, but it doesn't mean it's right. But aside from, typing it in again and double, triple, quadruple checking my algebra one more time, 2 more times, 10 more times, if there's a mistake in there, it's not easily found, because it's just typing it into Desmos. That's the bear. It can be tricky when it comes to that. All right. So then the last thing I wanted to do was number 6. Number 7 is a little bit beyond. That's more for the next unit, because we actually that we start getting into cylindrical and spherical coordinates with that. That number 7 is actually the teaser. It's sort of like the motivation question to get you thinking, man, I wonder if there's an easier way. And there is. It's in unit 3, but that's a different problem for a different unit. All right, but for now, number 6. This is really kind of my favorite question, because if the other sorts of problems don't really motivate you to understand or to learn why the order of integration matters, then this one usually gets the job done. All right, because we look at this and we say, all right, we're going to evaluate the iterated integral. Doesn't look like too crazy of a problem. So maybe you dive right in. Maybe you say, I'm not going to switch the order of integration. You say, I'm just going to jump right in and go right to town on this. And immediately you hit a roadblock. You're like, oh, I know how to take the derivative of that, but the antiderivative? Yeesh, I don't know. Then it's like, all right, well, what about, well, maybe I'll just take a guess. All right, what about integration by parts? What about some kind of substitution? It's like, before you know it, you're like, you're staring at the problem. You're like, how could something so simple be something that I just can't do? Now, if that y lower bound was a numerical lower bound, then it'd be fine. You put it in the calculator. But if you think to yourself, wow, this would be a whole lot easier if this said, whatever the 2 bounds are, e to the x squared, then the dy followed by the dx. After you go through the first round of integration, you look at this part would be nice and easy, because e to the x squared is treated as constant. So you're looking at it as e to the x squared y over whatever the bounds are going to be. It's not just a matter of saying, well, I'll just make that the bounds go from 0 to 1 in the place of y to 1. It doesn't work that way. And you might even look at this and say, well, I'm going to be right back to where I started after I do this step, because then I still got to integrate it with respect to x. And that would be true if you had to do it by hand. But if you have a graphing calculator, then it'll do it for you. So I'm not worried about that. Right? But what we need to do is figure out what bounds are most appropriate. Right? So I'm going to draw an XY plane. The original bounds were in the form of x equals so x equals y. Now, as I wrote it, it kind of looks an awful lot like y equals x, which should be easy enough to graph. I'll write it both ways. X equals 1. So I'll just kind of throw that over here. All right. Then for the second iteration of the integration, it would be y equals 0 to y equals 1. All right, so that's going from the x-axis on up. I'll just kind of shorten that up. I never should have brought that one. I never should have brought it with me. All right. So we have our bounds, really. I mean, just doesn't seem like they're really much of anything to be impressed by, but they're there. I'll make this purple. Make it pop a little bit more. All right. So we want to be thinking about what they wanted us to do initially, but what we want to do instead. All right. So they're saying go from the diagonal line in terms of x. Go from the diagonal line to the vertical line, x equals 1. Right. So x movements. Right. So if I were to say, like, for example, if I were going from x equals 0 to x equals 1, that would be easy enough. I'd be saying, all right, I'm starting off at x equals 0, which is right here. And then I'd be going x equals blah, 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 blah. And this would be me progressing from x equals 0 to x equals 1. All right. Well, what this is saying is, okay, well, we're not doing that, but we're not too far off from that. All right. We're going from the line x equals y to x equals 1. All right. So, and then from there, we're going from y equals 0 to y equals 1. So what we're doing is we're kind of creating a restriction where we're saying, and let me get that purple up, that I'm capping this thing off at x equals y. So I can go no higher than that line. But I can go down as far as I want. Slanted on me. I guess that's fine. Then I'm going from 0 to 1. So starting off with these horizontal lines, the horizontal line is 0, I'm going upward from there. The intersection of these two regions gives us what we want. All right, so that's how they set it up. That's what their notation meant. They're bound, they're given bound. Now, what we want to do is transform that into what we want. All right, I can't get that last one to fit, so I'm just going to move this one over and kind of split the difference. All right, so the x values, normally it would be in the form of x equals something, you know, like x equals 0 or x equals 1 or x equals 0.5, x equals -2 or something like that. All right. X is boundless in that it would go up and down forever. But what this is telling me is that, yeah, it's boundless, but under normal circumstances, but we're capping it at the line y equals or x equals y. So we want to think about it the right way also. All right, so this really is the line x equals y. So if I'm changing my perspective, all right, so it's the same region we want to capture, but now I want to be thinking about the y first. All right, so I'm going to redraw my picture and live with the insane amount of regret of not having copied the entire diagram first. And that last little bit, I'm just going to leave that there for now. Good enough, good enough. All right. So same diagram or same bounded region, and it'll ultimately be the same sort of diagram, but this time I want to account for the y stuff first. All right. Now that y, again, the innermost integral should be a variable integral, right? So if I'm working my y's now, and I want to get through to this interval, I want to cover the same region here. I still want to start off at y equals 0. But now it's more like, well, I'm restricting based off of the function y equals x, right? So now we're thinking of this as y equals x. Now, I only want the part of it that actually makes sense based off of the area that I'm looking for. Now, there would be a question, I would have this question, like, how do you know to shade this side, to draw the lines on this side, the portion of the lines on this side as opposed to the other side? Well, that has to do with the restriction that we're creating, right? Because like, you're kind of looking at it, looking into the future and saying, well, we already know that we're going to be also restricting the x so that it's in this interval. So between the restrictions for y followed by the restrictions for x, this is just how it's going to play out, right? So it's kind of like a little bit of, it's sort of cheating a little bit, all right? But then in terms of the x values, we're going from 0 to 1 without restriction. It's still going to cover the same region. It's just going to be in a slightly different way. My pencil's skipping here. So we're looking at the bounds for y should be going from y equals 0. You think about the lowest y that we had available to us. It was y equals 0. Going up to y equals x. You put the little y's in there. And then we're restricting that to go from x equals 0 to x equals 1. All right. So now we know that we're bounding again from 0 to x. Easy enough. We're looking at x e to the x squared dx over the interval of 0 to 1. Yeah, you could do that by hand with a little bit of u sub, but I don't want to. How about antiderivative over the interval of 0 to 1 x, parentheses, x e to the x squared. Close it up, slap a dx on at the end, and you have it at approximately 0.859. All right. So again, it's that weird interaction between the two sets of bounds yeah, you're going from y equals x to, well, it was really from y to 1. We're thinking of that as x equals y to x equals 1. You want to think about what that means visually, right? Because x could be anything, but if we're capping it or we're restricting it to only instances where x and y are the same, that puts it on the line, right? And we only care about the relevant part of the line based off of the restrictions for y that go from 0 to 1. So that brought it below the line rather than above the line, right? So like I said, that's where we're ending the unit. The practice test is up. If you have any questions related to that, definitely ask, send me messages, whatever. If you need me to do a video solution for something, send it to me. I try to get turned around on that stuff pretty quickly, but sometimes life gets in the way, but I'll try my best. All right. So, but like I said, if you have any questions, just reach out to me. It's better to ask before than after, obviously. All right. So let me stop the recording.